Can you help me take this out of the cover?
What's wrong with it?
The cover kind of muffles the sound a little bit. So it's just easier to remove it. Because I've noticed that in the past.
It's the wrong time to do it. We have to get started. Yeah. Is the sound active now?
Yeah.
Good. Excuse me. We will. As soon as we get ahead. So welcome everybody to our phenomenal physics show. The applause should be for all of you who love science, because really, I love being in front of people who love science, and even the people who don't, they love science by the time we're done. Two things before we get started. Everybody should have a pair of these. If you don't have them now, don't worry. We're going to hand them out when we need them for the demo show. They're diffraction grading glasses, and you'll need them, and Rutgers is giving them to you for free. And when is the last time Rutgers gave you anything for free? And then there's this sheet right here, and this sheet right here has all the information about the demos we're doing. You can go to the website that's listed on it. And if you want to write thank you letters, which help us a lot, then you can do that to all the people that are listed on this this sheet right here. Those are also out on the main table that we have outside. So, I'm Dave Mayulo, and I built and designed and put together all these wonderful demonstrations, but one of the loves of my life is really working with these brilliant young people that you probably saw outside doing all those wonderful demos. And here they are over there, and here they are over here. Bring them all in. Every year, that cast of students that I get to work with, I'm so privileged to get to work with, that changes all the time. But these people are the ones who give me hope for the future. And there's a lot of reasons to be a little depressed about the future in ways, but these are the people who make me think we can get through almost anything, because they're that great, okay? And before we get started anymore, David Sheet, our special guest star, is going to say a few words.
So, welcome everyone. I'm David Shee. I'm a theoretical particle physicist here at Rutgers. And so I'm a theorist. Usually you would not be anywhere near any of the sophisticated, delicate equipment. Yet here I am to give a special shout out and welcome to the students and families of Amsterdam Elementary School in Hillsborough, where my son is a second grader. And the reason for the shout out is that they just finished their annual science fair, and this year's science fair theme happened to be physics. So the organizers and I thought it would be a great opportunity for the students there to get to experience these amazing demos that Mark and Dave have spent many years perfecting the art of. So I'll just mostly be a prop for the day, and I hope everyone enjoys the show.
Well, David is actually going to do our very first demonstration. You know, we kind of build physics as a story, and we start with Newton's first law, because it's just so important for the principles of physics and all the things we do, you know, after Newton's first three laws. So what we have right here, we got some plates, right? We got this flowers, which are so pretty, and a candle that's, oh, if we lit the candle, you're really in trouble. And we have all these objects on this tablecloth. Now, if David moves that tablecloth very slowly, what happens to all those objects? They move. Newton's first law tells us they can only move once a force acts on them, okay? But what David can now do, he can actually take that tablecloth and he can pull it so fast it actually overcomes that force of friction that allowed them to move on the tablecloth. Do you think he can do it? No. We just taught him this 10 minutes ago. Let's see what David can do. Yeah! Now everybody, Mark Crum. Let's say hi. ready for the buzz magnets.
Okay. Oh yes. Well, actually, it's the second law, but we do the moving. That was the first demonstration was a demonstration of objects at rest tend to stay at rest, like me on my sofa, where my wife wants me to do work. And the second one is the same thing. It's objects in motion tend to stay in motion, uniform motion, in a straight line with constant speed. And so this would have been around a couple thousand years earlier, but they didn't have hovercraft in Aristotle's time. Constant velocity is in the same direction. And this is the same as objects tend to stay at rest. Now the next one is the famous F equals ma law. That is, you exert an unbalanced force on an object, and it changes its state from not at motion or constant speed. It gets a velocity. It has an acceleration. And so if you have a low mass object, the mass of an object is its tendency to resist acceleration. If you see a big lineman in the NFL, they don't get moved very easily, okay? Well, here's a very light object. I exert a force on it, then it goes shooting off very fast, has a large acceleration. Here's a larger object. Sitting in the front row is always not a good idea in this case. Okay, and so it goes a little bit faster, but this third guy in the front row doesn't have to worry about it because he's made out of lead. And friction along with his leadness makes it not move. He doesn't like to accelerate so much that I can beat on my hand and it doesn't hurt a bit.
You want to hear buzz magnets now?
Oh yes, yes. I've got one other thing that I usually like to emphasize at this point, and it's something that Newton knew from Sir Humphrey Gilbert, I believe it was, who did, and other people, they did experiments on lodestone magnets. And the wonderful thing about magnets, it's difficult to get the sense of action at a distance in gravity because the moon's up there and it might be more magical. But if you have a magnet and you put them next to each other, you see they snap together. Something reaches out in space and they pull themselves together. Action at a distance. That's extremely important.
But we do have the third law, and our third law is every action has an equal and opposite reaction. I call it the marriage law, but for a whole other reason. So for that, we're going to describe how you've probably seen it in the past. Because what I have right here is a balloon. And I bet you've done this experiment by yourselves. All you have to do is fill this balloon with some air. Now I have air in the balloon. If I let it go, what does the balloon actually do? It races in one way. What does the air do? It goes the other way. Action, reaction. So we actually have Newton's third law with a balloon, just like that. Okay? But that's not so impressive. Let's try the same exact demonstration with this. What's this? Fire extinguisher card, exactly. Right? There's a nice big fire extinguisher. Now please, after watching me do this demonstration, don't go into the hallway and grab a fire extinguisher and try to rock it around the room. It ain't gonna work and you may get arrested. Don't do it. At the same time, I can put this fire extinguisher right here. And you know I have a sail on my fire extinguisher card. I'm gonna take all the force in the fire extinguisher and I'm gonna put it on that sail, just like that. So, I want to know, let's do a physics survey. Who says I go that way? Think about it. Good. Who says I go that way? Excellent. Who says I go this way? Good. First astronaut. Who says I head this way? Sooner or later, not today. Let's go. By the way, this is an extremely loud noise. If you're scared of loud noises, especially you here in front, you might want to cover your ears, okay? So let's see what happens when I hit this fire extinguisher, okay? 3, 2, 1. Which way did I go? Nowhere. The only thing that happens is your butt gets really cold. It goes right down your shorts. It's one of the things that happens, except this. Why didn't I go anywhere? Well, that law tells us we can't push on ourselves and go in any motion. That's not how this law works, right? But here's what we can do. This is why we have Musarat. Because Musarat's going to stand right behind me now with this sail. Which direction is this fire extinguisher cart now going to go? Once he pulls the sail out. Pull it out, Musarat. You're right behind me. There you go. He's ready. Which direction? That way, exactly. But he's going to stand behind me with that sail. What's going to happen to him? He's going to see an awful lot of force too, because there's a lot of force in this fire extinguisher and our cart. Okay, let's see some rocket motion in action. 3, 2, 1. Just like that. And Mark has something to show you from his recent past.
Yeah, recent past. Well, I sort of invented this demonstration, but we didn't have a cart back then. So if you look up here on stage right, you'll see the way I used to do it. There I am with a 50-power fire extinguisher, and I have a pair of racing skates on. I was a little younger and more foolish then. So let's start it. It takes me a while. Yeah, I get rid of my glasses because I have health insurance and my glasses insurance. Okay, come on. Hurry up, Prof. Come on. It makes me nervous whenever he watches. I shot that fire extinguisher in a rather odd way. It's not because I'm odd. That doesn't necessarily mean I'm not odd, but because I learned early on, and I'll talk about this, if you don't hold it carefully and shoot it, it turns around twisted. And I have to tell you, the first time I ever did this experiment was for an astronomy class over in Hill Center. And I had a little teeny fire extinguisher and an old pair of skates on a rug floor, and nothing happened. And I got so ticked off, I showed up the next time with a 50-pound fire extinguisher, a new pair of racing skates, and to my everlasting, the low point of common sense of my whole lifetime is I got up on a table about this tall. And I didn't know quite how to hold it, so I blew myself twisting and translating off the table. People cannot believe I survived that. I myself. Okay.
So we have Newton's second law, which is force is equal to mass times acceleration. Fantastic. All right, so we're learning. So let's see another example of that. Because what I have right here is this long plastic tube. And inside this long plastic tube, I have a ping pong ball on one side. Okay, just a ping pong ball. On the other side of this long plastic tube, I have these 3 cans. They're soda cans. They're empty, but they are soda cans. What I'm now going to do is take all the air out of this long plastic tube. Now, here's what's going to happen. Now that we've removed most of the air from that long plastic tube, I'm now going to take this, a very, very, very sharp blade, and puncture the side of the tube. When I do that, the same force of atmosphere that's pressing down on your bodies right now, which is an awful lot of force, is going to re-enter the tube on this side. When it does that, it will then take this ping pong ball, which is inside it, accelerate it down the tube, and when it leaves this side of the tube, it will be going 700 miles an hour. That's how much force in the atmosphere is. But what's right here? Soda cans. What's going to happen to them? I say we find out. By the way, this is also another very loud noise. 3, 2, 1. What did we do? What did we do? Did anybody see the ball move through the tube? No. 700 miles an hour is actually pretty quick. Wow. Soda can number 1. I can see it through the soda can. Soda can number 2 getting burnt to a ping pong ball. And it kind of dented the margarita can, which is good because I'll use that later. Mark.
Okay, so that's objects moving in a straight line. Newton, of course, studied all this stuff, but what he was really after, in many ways, was the laws of planetary motion. And the planets tend to move in circles. And so let's talk about circular motion. The nice thing about this, here's the ball. I'm going to swing it around in a circle, and let me just swing it around once. You see it moves in circular motion. The really nice thing about a rope is I can't push with it. I can't do this with it. I can't do it. All I can do is pull on it. Okay? So that means as it's going around in circular motion, the force always points along the rope, towards the center of the circle. That's what keeps it moving in uniform circular motion. And if I, whoops, we're down to some, okay, I can do it this way. If I let go of it, it will go off tangential, and this will be the David and Goliath effect. Watch out downrange. Okay, it goes off tangential. It gives you the sling effect, okay? Now,
David has another way of showing that.
yes, except he's going to do a demonstration of how objects going around a circle get pinned into whatever they're in. Do you want to talk about it? I can hold your mic for you.
David's got some water right there, and he's got his bucket right there. He's going to pour the water into the bucket. Now, how can David put that bucket of water over his head, upside down, and not get wet? How can he do that? How can he do that? He can actually swing the bucket. So let's see if he can do this.
Stand closer to the front row. He is a theorist, remember? Okay, it's my turn, I guess.
Mark's got a much more frightening way to do this.
Yeah. And I won't stand too close to the front row. Dave insists that I do this demo. It's because I'm not very good at it. Put it on. Is the mop ready? We used to have a longer one of these that I was better at.
Which is why we shortened the string.
We used to use champagne too. But I never got a drink, so we stopped using champagne. Okay. Blue like my shirt. I guess that's good. All right. Let me see if I can swing this around in a circle without getting everyone wet.
No way. No way.
By the way, we'll use this a little bit in a while. Actually, we're going to talk about energy, so we can move right into it. In my younger days, I used to play lacrosse. Lacrosse comes in with circular motion and centrifugal force to pin things in because the guys who play lacrosse use it all the time. Remember when they come downfield, they're going like this as they're running. That's because they're doing it in circular motion and pinning it into the net, into their stick with centrifugal force. And when somebody comes up to hit them, they do it really fast. So the force is even larger so it doesn't get dislodged. Okay, so the reason I really have this out here now is we're going to talk about energy now. And when you have the concept of potential energy and kinetic energy, and lacrosse is a good thing to do that. Because if you take one of these guys and you throw it really hard, you'll get kinetic energy, energy of motion. You don't want to be in the way. On the other hand, if I take it like this and I hold it up very high, it now has energy of position. And energy of position can be converted into energy of motion just by letting gravity take over. So I started off at a low height, and it hits the floor at slow speed. If I hold it at a high height, it hits the floor at a much higher speed. Okay? So that's conversion of energy of motion, potential energy of gravity into kinetic energy of motion. Now, that it so happens that there's many systems in the world. Yeah, pendulum and string. Okay. There's the pendulum. The conversion of energy to motion and motion to energy and back and forth can occur with a characteristic time. If you have a pendulum it has low potential energy at the bottom. If you give it high potential energy here, it will have a high potential energy, and when it gets to the bottom now, it will be moving. Potential energy, kinetic. Potential, kinetic. But I can't say it fast enough. So it goes back and forth, and it has a characteristic time that it converts that. If it's a nice short pendulum, it wiggles back and forth quickly. Okay, so that's the idea of a pendulum clock. The same thing happens with a spring, and
Spring and mass, right?
here it is, it's another cross there. Okay. Here is an object. Stretching the spring gives you energy. In other words, it might do this, like exercises and catch chest hairs and pull them out. That's greater and smaller potential energy of stretching the spring. But now it goes from potential energy of a stretched spring to energy of motion and back and forth with a characteristic time. And for later reference, there's a phenomenon we call it resonance. If I wiggle this thing up and down slowly, nothing much happens. If I wiggle it really fast, nothing much happens. But if I pull on it very close to its natural way it likes to transfer potential to kinetic energy, watch what happens. It can shake itself apart. Okay? And so if you match your frequency to the vibration rate of the object, you can get it to build up and up and up and give you problems. Okay, now, all right.
We're putting David in danger one more time. And for this, I want you to look at the screen that we have right here. We have a cinder block down there. And what I'm going to do is give David this big pendulum, which is actually very heavy. He's going to put it right against his face. And you know, I just took that pendulum, I did some work. By adding energy to it, you're doing work. And I did work, I lifted that pendulum up. That pendulum, by not moving and being right against his face, has lots of potential energy. But David is now going to release that pendulum, let it swing on down, and all that energy at the bottom of the swing is kinetic energy. But what's right there at the bottom of the swing? Cinder block. What's going to happen to our cinder block? Let's find out. David. Oh, yeah. Well done. Well done. But here's the dangerous part of this experiment, besides being on the ladder. David is now going to take this pendulum, he's going to put it right against his face. He's not going to move. He's going to let the pendulum go. It's going to go swinging way down over there. It's going to come swinging way back. Should he be worried?
He's not worried. He knows the theory of it.
Let's see what happens.
Did you lean forward?
Well done, sir. Well done. So Mark just showed us a little bit of energy and what we call resonance. And kids, once in a while in your lifetimes, your parents are going to bring you to a really, really good restaurant. And when they do that, these glasses are going to be on the table. And the waiter knows you're too young to have any wine, right? That's a wine glass. So what's the waiter going to do? He's going to take it away. Don't let this happen. Instead, you take that glass, you put it right down there on that table. You take your fingers, you put it right in your dad's water glass like this. And then you go ahead and you rub the top of that wine glass. And you get a really, really pretty tone out of it. You hear that? That's quite nice. But what's the best part of doing this experiment in the restaurant? You're going to be bugging everybody, including your parents. Your parents are going to be like, knock it off. And you're like, hey, I'm doing physics. I can do this all day long. Right? So you do that for a while, and then the waiter, right? The waiter's like, hey, what are you doing? This is a quiet restaurant. You know, we have some standards here. You say, waiter, I've got a question for you. So you go to that waiter and you say, I'm going to take all the water in my dad's water glass. I'm going to go put all that water in that wine glass. Does the tone change?
Yeah.
Does it go higher or lower?
Lower.
You sound just like the waiter. Because they do this in restaurants all the time. It is now a lower tone. A lower tone because you now have the density of the water mixing with the density of the wine glass, actually giving us a lower resonant frequency. But you still get to bug all the people in that. But right here we have a beaker. Okay, it's right here. And I'm going to actually move this over. Do it just like that. Can you see that beaker?
Yeah.
Yeah, you can see it down there. And actually, I think it's actually even in focus, which is great. Could you hang this thing up over here? We need someone tall. Okay, so what I'm going to do, I can actually tickle that beaker in there the same way that I did with my finger on this. I can do it though with sound. I can play a sound. There's a speaker next to the beaker. I can make it rhyme. That's just how it is. And I can actually make that beaker ring. And you can hear that. But here's what we can do. We can give it way too much energy. And if we do that, what happens to the beaker? It may just break. Now, we're never quite sure if that's going to happen or not. So here's what we're going to do. First, I'm going to actually turn on a strobe light and turn off these lights and turn off the lights that are over you. Okay, now we're going to look at that, and you can even see it already shaking. And it's shaking pretty violently, isn't it? So let's give it more energy and see what happens, okay? Break the beaker with that sound. There you go. I hope you like that.
Remember, we followed the way how the amplitude built up until it started getting out of control. That's exactly what happened.
Look at it.
They very carefully tuned the frequency to match that with the beaker like to vibrate at.
You're on HDMI 1?
HDMI 1, and I need it on right and left.
There we go.
Are we going to do the rod?
Yeah! You ready for that? We need
Talk about waves first. Are we going to talk about?
Yeah, you talk about it.
Okay. All right, now we're going to talk about waves on objects, and sometimes it can be on solid objects. And the point is that what we have in the room right now, me talking, is sound waves propagating out to you. Now, a sound wave is a pressure wave that vibrates up and down, but here's a wave on a string. And you see it moves, and this is a very high frequency wave, and if it's a sound wave, I would say it was like this. That's really, I know I have a great voice. I hide it well. This, on the other hand, it has a very short wavelength and a high frequency. Vibration rate is high, and the length of repetition is long. Now, if I go over here, I have a low. Okay, so now what I want to go is to a low frequency. I go from E to. Okay, that's a very low frequency wave, and you see the wavelength has gotten very long. Now, it so happens that if you have solid objects, and let me see if I have this simulation here. Yes, here I have a simulation of the vibrations of waves on a string, and I'm going to start them. Start. Oh no! I can't see very well. Reset. Start. Yeah, I better start it over here. My apologies. Reset and start. There it comes. It will take a little longer now. Here is a wave, and you see it's moving along, and it's coming in from one side, and what I want you to notice is when it bounces up here, it heads back the other way, and it interferes with itself. Okay, what was coming in and what is bounced back, they add up, and you see a wave swings positive and negative, and sometimes you get zeros. And so when I wish it was faster, but there it comes back, and you see the black is the result of adding up the two. So you see they give you this one, before the peaks were always moving, and there's still right moving peaks and left moving peaks, but this black one is always in the same spot. And this is what we call a standing wave. And this is the thing that you get when the wavelength of the wave is comparable to the length of the object. When it fits just right, it has a resonance condition. And so Dave is going to do this now with a...
Well, we're going to use a rope slinky first. For this, I need a volunteer. Anybody want to help me? Got to be a little bit older on this one. Come on down, Patty. Come on down. I love that. I love that. Come on down. Oh, no. Okay, Patty, this is a very, very important experiment. We have to do this just right, okay? I want you to
better
stand
nails, right?
Right over here. Right over here. You look this way right now, okay? There's three things you got to do, Patty, okay? These are all very important. First, put out two hands and hold this really, really tight. Okay? Hold it really tight. Hold it about this high, too. Hold it nice and high. Good. You're ready. Okay, also, Patty, when I ask you questions from the other side of the room, can you answer those questions? Can you be loud, Patty?
Yes.
Okay. Prove it. Say something really loud.
Hey, physics!
That's it. So she's got this. This is great. Okay, good. So Patty, okay, this is the most important thing out of all my instructions. Whatever I do on the other side of the room, don't let go. Because if you let go, I get hurt. Okay? So I'm coming way over here.
What temptation.
Lift it higher a little bit. That's it. Just like that. Good. Okay. Patty, do you feel a little pull right now? Just a little pull. Not much. Maybe. Just a little bit. But of course she does. This is a long spring. You ever pull on a spring?
Yeah.
You feel a little bit of a force, right? So Patty, hold on tight. Try not to move. I'll do all the motion, okay? What kind of motion is this, everyone? What is it? It's a wave. This is a wave. That's exactly what we have right here. You know, this is wave motion, okay? Waves are so important to the universe, to light, to sound. It's a huge part of physics. It's a huge part of life. And you're seeing one right now in a rope slinky. Let's check in with Patty. Patty, do you feel a little more force now?
Yes.
She does. But notice this. The rope slinky is not moving towards Patty or away. She still feels all the energy of the motion. And the secret and beauty of waves is the energy travels, but the medium doesn't go with it. It just lets that energy travel across the medium, our rope slinky. Now, Patty, hold on tight. Try not to let go, okay? All right. We now have two waves where we used to have just that one, okay? Patty, do you feel a little more force right now?
Yes, my arms are.
Yeah. And it's true. The smaller the wave, the more energy we have in it. And that's true in light. That's true in sound. It's true in rope slinkies. And she's about to fall over, so we'll stop. So here's this great big rope that we have right here. And just like that rope slinky, I can give it a little bit of a pulse, just like that, and you see that pulse move back and forth across the rope. Well, here's what I'm now going to do, and Mark will talk about all these effects. I'm actually now, want to get through there, buddy?
I don't think I'll fit.
I'm going to tickle it over and over again. And we can give ourselves, once again, that first wave, that fundamental.
Remember, a wave has maximum and minimum, and if the length of the wavelength just matches the halfway length of the exact length of the rope, you get the first standing resonant wave. It's like if you have a guitar string, it's the lowest tone that you can get on that guitar string, and it has a maximum in the middle. It has to have zeros at the end because we can't waggle the walls of the table, okay? But it has a maximum in the middle, so that's the first frequency. The second frequency, we believe goes a little faster, the wavelength gets shorter. And you see now, it has a zero in the middle, and it has two maximums, and that's the second standing wave, that's a little higher frequency. That's the first, the next harmonic. Now, with the still higher frequency, you see the wave fits into the length it has to live. And that's when it gets fixed. 2 zeros, 3 maximum. And I stopped there, but I think they never stopped.
More power.
That's 4. Can we play higher than that?
Of course.
the basis of all quantum physics. Except it's not a string, there are electron waves, and they fit around atoms exactly of their length, and that's how we have stable energy levels for atoms, resonant waves like that, stable waves, and they can't make transitions or have electrons around them except in those states. Now, are you going to do the singing Ron, or are we going to skip this?
Let's do it.
Okay. Dave has the magic touch on these things. I would often do these things and get them wrong. Not only lets me do the stuff, it gets me wet in a mess.
So, it's springtime, and that means everybody wants to spend a whole lot of time in Home Depot or Lowe's, right? Because you go there, you buy a whole lot of stuff, right? And if you walk down that one aisle in Lowe's or Home Depot, you're going to see these things. These are just aluminum rods. So here's what you do. You go ahead and pick up that aluminum rod, and you hold it right in the center like I am right now. You have to bring yourself a little violin and rosin when you do this. Okay, you get a little violin and rosin. Violin and rosin is just the sticky stuff they put on the bow, you know, to make a little bit of friction. You hold it in the center, you take your other fingers with the violin rosin, and then you go ahead, and you do this. And you watch all those faces in Home Depot and Lowe's. Is that the fire alarm? Is there something going on? No, I'm just rubbing mine raw. And you do it just like that. And anybody can do this. Anybody. It's not that tricky. And that's a pretty sound.
Yeah.
And I can actually do this too. Oh, you want to talk about it?
Let me just show it. You notice he's holding it in the middle, and it's again 1/2. It's exactly the length is 2 times a quarter wavelength. It's a half wavelength, except you have to have maxims at the end instead of zeros now. It's the same, it fits. The wave that's right is the wave that fits on the rod, or the string that is vibrating. So the next one he's going to do, you see he's going to...
Well, first I'm going to do this, Mark. First I'm going to do this. Again, I'm going to put my energy. Remember, this is all just energy exchange. That's what it's really all about. I take my energy, I put it in the rod, and it rings. But I can take this cup and be really annoying. That's why speakers are shaped like this. It's a great way to couple sound energy to the air. That's exactly why they look like that. So I can now move my fingers, as Mark said,
okay.
right up to that spot.
Right here, in here. Well,
Now-
you're going to switch, right?
Well, I'm going to switch, but, 3 things can happen, right? Actually 4. Could be the same sound. It could be no sound. It could be a higher sound. It could be a lower sound. Scientists, what's it going to be?
Higher.
I encourage you to go to Home Depot and find out. So here's what I can now do. It is actually higher. And we even found that note on the other side.
Yeah. He transfers fingers from here to here and doesn't kill it.
It's now a smaller wave. Remember, smaller waves, higher sounds. Just like that, 2 notes.
Grab it in the middle now.
The notes used to be in the center, but now that dies.
It kills it when he grabs it in the middle.
And now we can annoy all the dogs in the neighborhood. I know, it's really annoying. It's a lot of fun. So, but those are sound waves, right? Oh, do we do the cannon first, or do we do the flame? You do the cannon?
Traveling slinky.
Traveling slinky.
Smoke rings.
Smoke rings, yeah, we do that before the finger. That's exactly right. So let's look at our most expensive demonstration. What's this? A garbage can. Yeah, it is. This is what Rutgers lets me buy now. I'm going to take this garbage can. I need someone to hold that can. Okay? I'm going to take this garbage can and I'm going to do this. And some of you who are down here in front may feel something, right? You felt something. Now, did you feel anything up there? No. If they turned around, and I'm not calling any one of you liars. You're not liars. But if they turned around and said, look, I felt something, just believe me, right? That'd be fake news, right? You need proof of things. You can't just go ahead and believe what people tell you. You want to do some science. You want to see the evidence of something, right? So, Shine here, she actually is holding a candle. And I can take the same device and I do it right, I can blow the candle out. So now you all know that something's going on, and that's the really important part of this. That's how we do science. We need evidence, right? But what science really loves to do is see what's happening here. We don't just want to see the effect, we actually want to see what's going on. So what I can do is put some theatrical fog in this garbage can. Now, theatrical fog is just glycerin we heat up, so it's really not all that dangerous or anything. It's a little annoying. But remember, this was happening every time I hit this garbage can. You just didn't see it. And this is why, to me, science is so much fun. How much fun is that? And who's and it's not like it's really expensive. So go to Lowe's or Home Depot and get yourself a garbage can. There you go. What's that shape? What's this shape? Oh. So I'm going to put this square on the front of my garbage can. Scientists, squircles, right? What are we going to? What do we need to do? What life is really all about? Do the experiment. So let's put a just like that. What are we going to see? Circles. The only stable shape is a spring. Smoke squares, they can exist for a couple milliseconds or so. It's the only really stable shape we can get out of the smoke ring cannon. Now, what we found out by playing, and really, that's the best part of science, really. I get paid to play with toys all day. And it's fun. But sometimes we come across something that's actually quite fantastic. What shape is that? I take that and I now put that on the front of this garbage can. It's an ellipse, right? It's an ellipse. What are we going to see now?
No, lines. Lines.
Unicorns, yeah, that's it. That's a good one. We found out, just again, by playing, by putting this shape on the front, thinking, who knows what will happen? It actually is the gravitational wave shape. Does anybody here know what gravitational waves are? They're those waves, right from gravity, two black holes combined somewhere, they send out a ripple through our universe. This is exactly what that ripple looks like. You'll see that smoke ring oscillating back and forth in its shape, just like that. And it goes back and forth, and that's exactly what we have in a smoke ring cannon. A cosmology demonstration. There we go. Now, here's my next question. How big is that sound? How big? Not big, small. How big? Show me. Like this? Like this? Like this? How come you don't know? Because we don't see sound. Right? We hear sound. You don't see the sounds you normally hear. So here's what we can do. Here in our show, we can show you sound. And how do we do that? Well, of course, we use fire. Come on in. Come on. Oh, it's this one.
Turn on to light the place on fire.
Who, me?
Oh, we have no problem with that. Long experience. We need the lights there, right? Should I turn them out?
Yep.
Oh, we turn them out over there. Okay, you got it?
Come on. It's got to fill that tube.
There we go.
Come on in. That's our gas. So as we fill this tube with that propane and we lit the top, we have lots of little holes across the top of that tube. And we got the lights down, which is fantastic. And now what I'm going to do is I'm going to turn that flame down to a nice manageable flame. Just like so. And now what I'm going to do is put that sound back inside and allow you to see sound. Because that's the sound. I'm going to take that sound, I'm going to go higher. Higher in frequency. What happens to the size of the sound when I do that? Does it get bigger or smaller? You see that one? It is smaller. Just like that. And I can go lower. And there it is. Look, this is why science is great. You get to see it, what you usually don't see.
And marshmallow.
And make marshmallow. We have the, we have this one. Oh yeah, you ready? Okay, David's helping us too. Come on, David. Lights up. Lights up. So we had sound waves there, but it turns out, come on, David. It turns out that you can actually affect sound waves with the gas. You can, your voice, right? So David has a balloon of helium. David, give us a, just say something.
Testing, testing, testing.
That's it. He's a theoretician. Okay, so here's what he's going to do now. He's going to breathe some of that helium, and let's see what happens to his voice. Go ahead, bring it all in. Take it all in.
How do you like me now?
Right? I hate to tell you that effect is perfect.
Oh my God.
That's it. Round of applause for David. Now it so happens I have a whole other gas right here. A whole other gas. And it's actually denser than our air. So predict what's going to happen to my voice. Lower. I know.
Radio voice. It's quite sexy. But this is what you can do in affecting how your voice sounds. I can change that sound as you see.
That's fun stuff. Oh, you want to talk about we're going to talk about yeah, why don't you talk about it?
Okay. If you put an object in water, it will either float and sink. If it's light, if it has low density, it will float in the water. If it has high density, it will sink. That is, if it's density greater than 1 gram per cc, which is the density of water. And it so happens that the force on an object is the water pushing on all sides of the object, and gravity is pulling it down. But if it is there's a buoyant force of the water pushing up on it, and if the buoyant force wins, it floats. If the gravity wins, it sinks. But it all depends on the density. Now Dave's going to do a demonstration here in which he uses different densities.
Here's a can of what? Diet Coke. I know some people who drink a lot of this. Here's a can of what? Regular Coke. You've all held these in your hands, right? So, since you've held these in your hands, you can easily tell me. I'm going to take the regular soda and put it in water. Does it sink or does it float? You don't sound like you know. What do we have to do to find out? Let's do the experiment. I put that can of soda right inside, right to the bottom. Diet Coke, sink or float? Right, this is diet? What kind of theory is that? It makes us lighter? What's it going to do in the water? What do we do to find out? It does. Do they give you less soda? Do they give you more bubbles? What's the difference between those two sodas? And there's no sugar in either soda. What makes this soda sweet? Corn syrup. It ain't sugar. And if you take it out of there, there's a good 1.5 to 2 inches of that thick, heavy, gooey syrup. inside that can of soda. And it's very dense, and it brings that soda right to the bottom of that water bath. What do they sweeten this one with? Rat poison. I mean, you just sweeten. That's right. They put that chemical in there, and they only need a little bit of that chemical to make it just as sweet as all that corn syrup that's in that soda. Which is why that's less dense than water, and that's more dense than water. But let me ask, where do you feel more of a buoyant force? In a swimming pool or the ocean? Ocean water. What's in the ocean? Salt. That's right. Toilet paper, lots of other things at the Jersey Shore. So here's what we do. We pour salt into this water bath. And you can now bring that regular soda right to the surface, because sinking and floating is all about relative density. There you go. Bring those balloons in, please. Bring those balloons in. Thank you, sir. I know, they're all so scared. Go ahead, unwrap that.
You know, when I'm out here to do the demonstration, that it's too dangerous for David to be too valuable. I, on the other hand, am expendable. Okay. Oh, yes, they blew an H on. This is a helium balloon. Actually, I can just use this. A helium balloon is the balance between the outward pressure of the gas on the inside and the elastic of the balloon. And there it says helium on it. And if I light it, what will happen? It'll pop. Okay, let's pop it. Now, why don't we turn off the light? This one is much less dense. What can be less dense than helium? Hydrogen. And hydrogen gets us into a little bit of chemistry. They keep making this balloon bigger. In fact, when I light it, you should see that it will burn vigorously. Remember the Hindenburg. Oh, there's going to be a bit of a boom here. I used to do that where I would hold the balloon like this until I figured out I had no hair left on my arm.
What were those balloons floating in? Air. What's in this drum? Air. What's in you? Air, that's right. Hot air, perhaps. But here's what we got. We have this big, heavy drum. And what I'm going to do, I'm going to have a vacuum pump connected to it. And we're going to show you just how heavy air is. I know we kind of showed that before with our ping pong cannon. But I'm now going to use this vacuum pump to take all the air out of this big, heavy drum. Don't be frightened. Sooner or later, that's not it. Sooner or later, that's not it. Sooner or later, that drum's going to collapse. Okay? And when that happens, it's going to be an awful loud noise. So don't worry about that. We don't know when it's going to happen. We don't have any idea. So we'll move on to the other demonstration, which is flowing fluids. Just ignore that. Mark, you got your fluid flow right here.
Okay. Here we have a little vacuum cleaner running in reverse, which is the way my wife is convinced the way I do it. And you see that the air shoots out and it can support an object on top of it. Barely. This is called the producer.
That was it.
Okay. So the air flowing out flows around the two sides, and it's not surprising that it pushes it up. But the fact that it doesn't fall off, that it's stable, is the interesting thing. And that's it doesn't fall off because it's a Bernoulli effect. fast moving air is low pressure, slow moving air is high pressure. So when it goes over here, it has fast moving air, low pressure, and it pushes it back to the side, inside. So the slow moving air is over here, high pressure, fast moving air, low pressure, and so it always pulls it back in. This is the same thing inside than the other, and that gives the airplane a lift. If you're going in on the train, the walls create friction, and so the air swishes by quickly on the sides of the train, and your ears pop because the pressure is changed by the Bernoulli effect. There's also another thing with the train. If you're waiting in the train station and a fast train goes running through, the doors swing out. They swing out because the pressure was lowered because of the high velocity air, and they pulls them outward, and the high pressure on the inside pushes it out. Okay?
What happened to our drum? It collapsed. You need to only take half the air out of a large steel 55-gallon drum before atmospheric pressure is strong enough to actually crush it like this. If I kept that pump running for a while, it gets smaller and smaller and smaller and smaller as we take out all that air. In fact, I pull the hose out, you can hear the air go back inside. But just like that beer can I crushed on my head last night is never going to bend for me to stand.
So we're ready for the
light. Oh, we do temperature first, yeah.
Yes.
That's right.
Usually Dave's the guy who keeps me on. Okay, now this is the one physics I really want you to take home and learn and have it at the tip of your fingers. It's the idea of temperature. We talked about energy of motion, right? Things moving fast. Well, here is a gas. And here is, you look at this is a very low temperature gas in simulation, and this is a high temperature gas. And what is the difference between these two gases? Here, the atoms, the molecules are doing what? Slowly, moving slowly. Low kinetic energy, low energy of motion. Big kinetic energy. That's all temperature is, at least for gases. It's a measure of the average energy per molecule in the gas. So if the things are moving fast, it's high temperature. If they're moving slow, it's low temperature. You now understand temperature for the first time in your life, perhaps, if you're quite young. And the zero of temperature, they are not moving at all on this scale. So you don't have to worry about the freezing and boiling point of water. The zero really means something. Everything stops. Okay, so that's the meaning of temperature. But you also have, you notice that these guys bounce off the walls quite hard. So they push on the walls, and the pressure is large. Okay, so that's why you have pressure on the walls of that can, because the molecules on the inside were bouncing off the inside. You suck all of them out, nothing's pushing on the inside, and they're still pushing on the outside. That's why they crushed. Okay? You can see when they hit the wall very gently, they push on the walls very little, and it's low pressure. So now you understand pressure also. It's just the average push of the molecules on the wall when they bounce off. And now let me turn on gravity here. So I got to come over here. Where's my mouse? There's my mouse. Okay. Is that gravity? That's gravity. When I turn on the gravity, what can you tell me about how many molecules I have at the bottom and how many molecules at the top?
All or none.
All none? Yeah, lots at the bottom and few at the top. If there's gravity, the molecules there'll be lots of them and they'll be at high temperature, and the ones at the top are at low temperature. But you knew that, right? Death Valley is really hot, fast-moving molecules, high density of air. Top of Mount Everest, you have to take your own oxygen up there. It's so low density. Okay? And so that's also something that you already knew in some way. Okay, so that's high and low temperature. Now we're going to fool around with temperature a little bit. And here I have some liquid air, liquid nitrogen. And by the way, I started off being a low temperature physicist in, actually we had Roman numerals and I can't quite remember. I think it was 1969. Yeah, 1969, 1970, something like that. So I'm quite used to hanging around liquid nitrogen. But you should be very careful. You should have all kinds of protective gear and all that sort of stuff. So don't just remember that. Okay?
Don't be a fool like him.
I'm at least inexperienced. Okay. Now the first one we do is first thing is we illustrate that it's really cold. And so we take some everyday items. We have a hot dog in here.
Nah.
Yes, I'm the hot dog.
Yeah.
Can you see what this is? Broccoli! It gets very brittle at these temperatures. You see I'm enclosed here so that way it gets scattered with this stuff. And what's this? Banana. What's that? It's a banana split. Okay. So things get very hard and brittle when they get very cold, and it's very cold indeed. Here I have a nice bouquet of flowers. And so, I should have started this going beforehand. So I'll let this guy start cooling off, and when I pull him out, he should be extremely brittle instead of being flour-like. In other words, a regular flour, you can squish it and it still stays intact. However, when you freeze it down, the liquid nitrogen temperature, it's brittle as glass. So that's an illustration of just how cold liquid nitrogen is. Now, this is one of my favorite experiments. It's a professor, I think. Here is a hydrogen balloon. If I would let go of it, it would float up to the ceiling. Now I'm trying to roll it around in liquid nitrogen, and when it's in the liquid nitrogen, of course, it will cool off. And I started going. What happens when I cool off a gas? What happens to the atoms? Huh? They move slower. Temperature lowers. Do they hit the wall slower or faster? So the pressure drops. And you see it's getting crinkly because it's shrinking down. That means its density is increasing. It's helium and it would float if it was its regular size. Let me see if I can get it right now. And now it doesn't float anymore. Its density is low, but then they start warming up, they get faster, they start having larger pressure on the wall, and eventually we need a bigger balloon. There we go, and now it floats again. Remember the illustration on the wall here. That's exactly what we did. Okay? That's why it's one of my favorite demos. Right here. You can actually see, oh yes, evaporated liquid nitrogen. If you take liquid nitrogen and you put it in a tube, it boils vigorously. And when you go from a liquid to a gas, the volume increases tremendously and the pressure will increase. And so that's why we call this the liquid nitrogen cannon. Okay, so let me pour a little liquid nitrogen in here and put a cork in it. Here, let me see if I can reach it. Watch out! I like to do this in class when my students are sleeping. This demonstration always reminds me of my father, because he worked at a nitroglycerin factory in 1930 here in New Jersey. up near Morristown. When he went in to get the job, they showed him his lab. They said, okay, you can go to work. And he looked around and said, well, why does it have 3 very strong brick walls and 1 wooden wall? They said, well, that's a blowout wall. What do I need a blowout for? Well, you're working with nitroglycerin, man. And so if you make a mistake, it blows up. It blows out the wall. We build a new wall, hire a new guy, clean up all the mess, and proceed. But if you're going to work with an explosive, you better make sure you're either in the open or have a blowout wall, because you also want to minimize the pressure surge. Okay.
Okay, so we're going to do those blocks. We're back to light.
Okay, back to light.
So right here is yours.
Light travels. Oh, yes. Okay, light travels at the speed of light, which is 3 times 8 10 to the 8th centimeters per second, which is very fast, 186,000 miles per hour. But when the light goes through a solid material, it slows down. And when it slows down, it bends its motion. So on the top, maybe you can give me a shot here. You see it coming in at that angle, and you see how it's broken as it goes into the glass. I can do it on this side also. There you see it gets reflected over here, but it doesn't come out here. That's called total internal reflection. That's how optical fibers work. Right, so you have the light stays inside it. If you have an optical fiber, I remember the first time I had a colonoscopy.
I bet you do.
That was so long ago. You kids that don't know what a colonoscopy is, it has to do with inspecting your intestines, and they don't go in through your mouth. And they used a pipe about this long. I thought it was this long, but it was only about this long. It was made of steel to straighten out my intestines. But the next time I came back, they had invented optical fibers, and it bent around to the shape of my intestine. I never appreciated total internal reflection as much as that moment. Okay.
You want to talk about this block and
Oh, yes, yes. By the way, I got this block by dumpster diving. The particle physics people were throwing I got called dumpster diver again. That's how I got my wheels for kind of momentum too. They were throwing this away, and it's a fluorescent material. If photons hit it, or other things hit it, it glows. And they were using it for, okay. If I hit it with green light, you see it just goes, it transmits quite nicely. But if you hit it with violet light, you notice how that dies off partway down. It's glowing also. You can see it very enough to get the electrons out of the atom. Here. I'm trying to be extremely careful not to get stray reflections into the audience, and this is a violet laser. And you shouldn't be handling violet laser. As a matter of fact, you shouldn't handle any laser unless you have a specialist that advises you on the 50 milliwatts limit. So don't fool around with lasers. Even stray reflections of some lasers can do extreme damage. Okay, this is now ultraviolet light, and you'll notice that the entire thing glows. This is why the particle physicists wanted it. Okay, because something with high energy would come in, and it would create a string of lights, and then they plot those, they pick up those lights, and they figure out what the object was and its energy.
you got some spray.
Oh, yeah. Oh, yeah. Where's the spray? Ah, yes. Oh, yeah. Usually, students like something that embarrasses the professor, and hopefully injures the professor, and it's a 3-horse parlay then if they get hospitalized. This comes under the embarrassing part. Does it show up?
Yeah.
Oh, yeah. Oh, yeah. Oh, yeah.
So now you can use this on the
Oh, yes.
here. That laser light is so powerful, it can put its energy in this phosphorescent sheet and actually leave that trail. Now, it's a purple laser, right? UV purple. Yet what color's coming out? Green. Green. So it's actually changing what it is, right? It's coming out as a whole different thing. He's pretty good with this. And you can see that, yeah, this is actually really good modern physics you're doing right now. Okay? So you have a different energy coming out after we get it excited.
Wait. Let me show him this. The green does it right. Lower energy, lower frequency. Higher energy, blue is higher energy, higher frequency. High enough energy to kick the electrons out of the atom and create this fluorescent effect. Okay? And that was the same thing that happened over here. The higher energy made it fluorescent, the green didn't. Okay?
Yes. Though you do have one thing right here.
Oh, yes. Oh, this is one of the great victories of modern science. It's a glow-in-the-dark toilet seat. But if you have the lights on and then you get in the middle of the night, it'll still have a faint glow to it. You can find it.
So we're now going to use those glasses. Does anybody need a pair of glasses? There's some people up there. Could we get them some glasses?
Just aim at my screen, okay? I'm gonna aim
Please
at
put
my
them on your face.
Okay. Oh, that's a short. Okay, now we're going to do some light. I teach astronomy now. Actually, I got the job of teaching astronomy by getting the telescope out last time Halley's Comet came through. Just in case you're not sure, that was 1986. And I showed the chairman Halley's Comet, and he looked at me and said, "You know, of course, you're going to have to teach next semester." I was a solid-state physicist, and I'd never even taken this course in astronomy. So I had a lot of learning to do. Okay, here I have a light bulb, and let me get out my diffraction grating goggles here.
We're putting this on the screen so everybody who's watching the stream can see it too.
Oh, good. Oh, I don't even need to put on my goggles. This is what we say a black body spectrum. It's called black body because it has essentially 100% efficiency at all wavelengths. The characteristic of the material, it's hot, it's dense, and it's just its temperature determines it. And it's hooked up to the rheostat, right? Yeah. Okay. Here is the light, and here are the spectra. These diffraction gratings have little scratches on them parallel to each other. Okay, and they separate light into its colors a little bit like a prism, except it does it by interference and much more efficiently. And so now let me turn down the brightness of the light. Let's start up there and see it's Roy G. Bibb. Red to violet. Now let me turn down the temperature, and let's see where it disappears from first. It's slow to react. Oh, what now? Yeah, okay, it was just a time delay.
Yeah.
Yeah, I was looking for it to occur. Oh, you got to turn it on more. There. Okay, stop. Okay, maybe we need two people. Okay, there's the Roy G. Bibb. Now turn it down, and it should disappear at the high energy part. See, it's fading away. Very slowly. It's got the red. You can stop. Now it's at low temperature. So you can tell the temperature of an object, specifically a star, simply by putting a diffraction grating on the end of the telescope when you look at it. And so if you go to very high temperatures, it has lots of blue, and very low temperatures, lots of red. If you want to look at the side screen over here just briefly, in astronomy, this red star up here in the constellation Orion is Betelgeuse. It's a red giant. It is only about 3,200 degrees Kelvin, and you notice it has lots of blue in it, and the belt stars do also, but this one is more red. You can physically see it's red. But down here in the bottom of Orion's belt, you can see it has a very nice individual lines. That's because Orion's belt is a glowing gas cloud of hydrogen. It's not a hot, dense object. And we can, go ahead.
Yeah, we can do a whole lot of astronomy just with this setup we have right here, because I'm going to turn this light on right here. What do you see above that first light that we had on? Another rainbow. But what's the top rainbow missing? Yellow. There's a black line where the yellow should be. It turns out we can coat the inside of this bulb with a material that absorbs that yellow. It doesn't let it reach you. And they make these bulbs on purpose because they think that human beings don't like yellow light mixed with their light. It makes it a little annoying or something. But this is actually absorption physics. Astronomers can look at, let's say, one of those gas clouds, and if we see a line in that gas cloud from the light that's behind it, we know what that gas cloud is made of. That's fantastic physics, and you're doing it right now with those glasses, and are doing it at home with the image we have up here. So now let's go ahead and look at some of these other sources. Mark?
Okay, the first one, of course, should be hydrogen. Ah, here it is. There's the spectrum. And you see it has some front in it, but it also has these distinct lines, a violet, a blue. But look at this red one right here. That's called the red bomber line of hydrogen. That's the famous one. That's the one that makes the Orion Nebula and the sword of Orion glow in the red. So this is the most famous and the most ubiquitous line in the universe, this red. By the way, Dave is not, I'm shining this on the screen, so there's no laser close to Dave.
That's right.
I actually flinch a little bit when I do this when somebody's nearby on the screen. Okay, so the next one up, this guy has a whole set of colors, but I want you to notice this yellow right here. That yellow right here is characteristic of helium. The same as our sun. Let me see if I can very quickly pull that up. It has to be fast to get to it. Yes, at a solar eclipse. Helium was first discovered in the spectrum of the sun. When you have a solar eclipse, they saw this yellow line that they'd never seen before. And that's why they named it helium, helos, for the sun. Okay? And so you've actually seen it now in person. And now what's the next one? Is that
The next one is
Mercury?
right here.
Okay, that's Mercury. And then we have a fluorescent light bulb with some mercury on the inside up here.
We can see the fingerprint of Mercury with that source, but you can actually see those same colors in the bulb because there's actually mercury gas inside the CFL bulb. Knowing what the fingerprint of any element is, we actually know what's burning. We can use these glasses to see what's burning, and they do this all the time in physics and in astronomy.
That's why you have to be careful about disposing of bulbs like that fluoresce, because they have some mercury on the inside. So it's a mercury solvent. This is neon? Or
Yeah.
This is neon?
Neon.
Okay, this is the honky-tonk cowboy color. Here it has a lot of red in it. So this is neon. And you can tell every element of the periodic table. If you make it into a gas and you tickle it with electricity like that, it has a unique fingerprint in its spectrum, because each of these correspond to an electron hopping between different allowed levels in the atom. Okay.
Turn that one off, and now we're going to show you just how much fun you can have with those glasses, because I'm going to turn that on. And watch as these lights, these LED lights change color. What are you seeing in the glasses than in the image up here? Light mixing in action. As it changes its colors, you can see exactly what colors are made up of the colors you see all together. It's rather fantastic. Please use those glasses. Look at a full moon. It's spectacular. It really is. Look at all the street lights. You can tell what gases are made up in the street lights. Look at many things in your house. Look at holiday lights. Just never look at the sun, please, okay? Because that will make you blind really quickly. Okay, so don't do that. Now we're going to use some other object we have right here. It's called a clear camera. For that, we need David's help again. Thank you, David. Hasn't David been a good sport? And we can see that image up there. Mark, would you bring that HDMI 2 over to the full screen? So I have David on camera, and we saw that before. We can turn the lights up a little, yeah. Because we can still see David with this. Okay? One side. So I see David, and David is glowing, isn't he? I mean, look at you. You're glowing too, yeah. This clear camera gives us temperature, right? And you're one hot audience. Look at that. And over here, yeah, wait, when's the last time you saw yourself in infrared? And you know, your faces are probably pretty warm, right? You see they're kind of glowing the brightest, and your clothing absorbs a little bit of the heat. But this is a measure of heat. But this is actually part of the spectra too, infrared, right? And David's right here on our screen, right? All right. And he's got, no, first please use the sign. Okay, that's great. But infrared doesn't look the same, doesn't work the same as regular light. Can you see David through that sign right now? David, point at them. Can you see him? Yeah, visible light goes right through that sign. But let me put this camera on David. He puts that in front of his face. Notice we can't see him now. Infrared light does not go through that plastic. Basically, it is blocked. Hey, you're in your car. Basically, you're getting nice and warm inside the car because basically the car heats up, but the infrared can't leave that car, right? So if you have the windows closed, how hot does a car get? Very hot, right? That's going to actually be dangerous. Now, David has a whole other object. It's basically a black plastic trash bag. And after seeing this, please don't go home, put a bag over your body. That's not a good idea. But can you see David through that black plastic trash bag? No, but we can put this camera on David, and we can still see him. That's right. It turns out infrared goes right through the black plastic, whereas visible light does not. Just trying to show you that it works a little bit differently. So there you go. Now we have our last group of demonstrations, and for this, we actually do need a volunteer. Lights all the way up, please. A couple volunteers. I can use some help. Couple volunteers. Anybody want to help me? Come on down. 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 Right down here. It's okay. Come on down. Are you scared? It's okay if you're scared. You want to come down? Come on down.
You can do it afterwards. We'll do the same thing afterwards.
This is Annabelle, everyone. Okay, she's going to help. Ellie, and this is Ellie right here. Thank you, Ellie. Annabelle and Ellie, do you two know what you volunteered for? A bed of nails. You never volunteer at a physics show. It's a really bad idea. At the same time, don't you worry. You're not getting anywhere near this bed of nails. Here's what we're going to do. My student Arnav and I are going to pick this up. We're going to move it right over here. Okay, now can I have that? Thank you so much. We're going to put this right here. And what we're going to do, we're going to take Mark. He's going to lie down right here on that bed of nails.
I can sleep on it.
That's actually true. Just like that.
It's getting on and off this time.
There you go, Mark. Wonderful. Now, Arnav and I are now going to take our second bed of nails, which has lots and lots of sharp nails. And we're going to put it right here on top of Mark. Right like this. Okay, now my two volunteers, please come on over. Yeah, just come on. That's it. And now we have two human beings. Turn around and look at your friends over here. Yeah! Two beds of nails. You can step off now. Like that. Jumping is always fun. All right. There you go. Move this one over. Now we don't do this. You can get up, Mark. Because David's not going to lie down on the bed of nails. Bring in those small beds of nails. Now we don't do all these demonstrations because it looks like magic. That's not why we do this. We do these demonstrations because it's all about science. And we really want you to understand it. So what we have right here is a demonstration of the bed of nails, right here. And this should allow you to explain why Mark hasn't been gotten hurt. I have something very similar to Mark. It's a thin balloon filled with hot air. Very similar. And here I have a whole lot of nails. Here I have fewer nails. Here I have even less nails. Okay? So here's what I'm now going to do. If I take this balloon and put it on that bed of nails, will it pop? What do we do to find out? Try it. Just do it. People are more scared of popping balloons than almost anything else in life, I think. Second bed of nails, will it break it? Can you use maybe in science? No. You have to come up with a theory. Will it break it? No. If that's for me, give it up. Will it break on the last one? Of course it will. It's the last one, right? And yes, it does. But think about the science this way. I weigh 200 pounds. Let's say I lie on a bed of nails. Where's my single? Is my single? Oh, forget it. Let's say I lie on a bed of nails with one nail. How many pounds of force on the one nail? 200 pounds. More than enough to drive that nail right through my body and kill me. Let's say I have 10 nails. How many pounds of force on each nail? 20. That'll still kill me. Let's say you need 16 pounds of force on a nail to go through human skin. I did the experiment. It was a bad day. Let's say I have 100 nails. How many pounds of force on each nail? 2. That won't go through your skin. It'll hurt. These all have 3,000 beds of nails. 3,000. So think about how little force there is on each nail, which is why we don't get hurt doing this the right way. But we have one last demonstration to show you, and that's why we're going to have David lie down on the bed of nails. Because we need to hurt him one more time.
Don't laugh. Get down slowly.
All right. And just lie down right there. He's never done this before. That's part of the fun. Just like that. And right on the pillow. Tickle.
Yeah, okay.
And we got the sign right here for That Is a Show. And I go back on stage in Broadway in mid-July, so if you want to come see me there. We put that right here on David's neck, and it looks just like a guillotine, doesn't it? Now, we take the second part of our demonstration. It's a big cinder block. We put it right here on David's rock-hard axe. And the last part of our is this, a sledgehammer. And here's our experiment. Bed of nails, David, brick, sledgehammer. Does David live? I say we do the experiment. You ready, David?
Whenever you are.
3, 2, 1. Plus the brick. A big round of applause for David. A big round of applause for Mark. A big round of applause for our students. Mark wants to show you one more thing.
No, it's not off.
No? Can you turn it off? Put your chest.
Get it?